Let's understand what these velocity time graphs mean. So, let's say that we have a car and then we want to consider the movement or the motion of that car. We want to check how the car is either speeding up or slowing down. It's going to constitute what we call velocity time graph. So, to keep it simple, let's say that this car started from rest. When we say the car is at rest, it means the car is not moving yet. So, obviously, the velocity is going to be 0. And the time where we start measuring is also going to be 0. That's the point of origin, where both the y and the x axis are 0. First of all, what's velocity? Velocity is speed in a specified direction, right? Velocity is almost the same thing as speed, just that velocity not just tells us the speed of the car, but the direction of the car. So let's say that this car started from 0 when the time is 0. Then after 1 second, the speed of this car changed to 2. In 2 seconds, it changed to 4. 3 seconds is at 6. Remember, velocity is measured in meter. The unit is meter per second, right? So what's going on here? Discover that as we begin to keep track of the speed of this vehicle, we discover that the speed is always changing for each second. So after every second, the speed is going to change. But now, the most important thing is that it's not just changing. You see that it's changing by equal amounts. If you can see very well, you see that this is 2. 2 is changing by 2, a factor of 2 each second. So after every second, the speed increased by 2 meters per second. So we have 2, then we have 4, then we have 6. Now, for the fact that the velocity of this car is changing, that's what we call what? Acceleration. So that's what we call acceleration. Anytime velocity is changing, we say that the car is accelerating. So acceleration is the rate of change of velocity with respect to time. So once velocity is changing, there's going to be acceleration. But now, the interesting part of this is that this velocity is not just changing, but it's changing uniformly, meaning it's changing by equal amounts for each second. So you see that it's always changing by adding 2 and adding 2. So once velocity is changing equally or uniformly, it's therefore accelerating uniformly also. So this type of acceleration is what we call uniform acceleration. So in summary, anytime you see that the slope of a velocity time graph is heading up in this direction, it means that this car or the body under consideration is accelerating uniformly, uniform acceleration. So take note of that. And then the acceleration of a velocity time graph, or rather, let me rephrase, the slope of a velocity time graph is the acceleration. So if you want to find out the acceleration of this journey, you just solve the slope of the velocity time graph, which we clearly see that is 2, but just to solve, we're going to identify 2 points, any 2 points of our choice. So let's call this our y1, along the y-axis. Remember, this is the y-axis and this is the x. So just call this our y1. That means our starting point, and this is y2, ending point. 0 also will be the x1, y3 will be the x2. So the acceleration is the slope, and the formula for slope is simply y2 minus y1 all over s2 minus x1. So acceleration is going to be y2 there is 6 minus 0, s2 is 3 minus 0. So we have 6 minus 0 is 6, 3 minus 0 is 3. So we have our acceleration as what? 2 meters per second squared, which is what we said initially. So that's how to calculate the acceleration. And you discover that the sign of the acceleration is positive. So anytime acceleration is positive, it means this car is speeding up. So it's increasing from 2 to 4. So this car is just speeding up. Now, the B part is the reverse of what's happening in the A part. So this is what we call uniform retardation. Since the car is slowing down, retardation is the opposite of acceleration. All right. If you don't, sometimes we call it deceleration. So it's still the same thing. That's the opposite of acceleration because this car is actually slowing down. So we can still call these points our 6 meters per second, 4, 2, and then 0, then 1, 2, 3. Time is in seconds. Uniform retardation always negative. So negative acceleration shows that the car is slowing down, and we can also calculate that to prove it. So since we are starting from 6 now, because we are starting from a high speed and we are coming down, so that point will be our y1, y0 will be our y2 when the car finally comes to rest. Alright, because when it's 0 meter per second, it means it's no longer moving at rest. And then 0 there will be our x1, while 3 will be our x2, because x1 is the time we started, is our initial time when we started measuring when we started taking notes of the journey. Then s2 is the final time before the car comes to rest. So acceleration there will also be y2 minus y1 all over x2 minus x1. So you see that our acceleration is going to be y2 is what? 0. So I have 0 minus 6 divided by x2 is 3. 3 minus x1 is 0. So it will be 0 minus 6 is, you see that that's minus 6 over 3. So acceleration is minus 2 meter per second. So you see that when we have negative acceleration, it shows that the car is slowing down. So if you see the slope going up, it means it's speeding up, and that's uniform acceleration. When it's going down, uniform retardation. Okay. So what of this third graph? What's happening there? You see that for this third graph, let's say that the speed there is 6, or since I've been using 6, let's say that's 6 meter per second now. And then you see that it's not going up, it's not going down, it's just going straight. This suggests that the velocity is not changing, so it's just at 6 meter. So this is constant velocity. So the velocity is constant. Now recall that acceleration tells us how much or how fast the velocity is changing. Now what happens when velocity is not changing means that acceleration is going to be what? 0. So acceleration at this point is 0 since velocity is not changing. So anytime you see a graph like this, it means constant velocity. So the acceleration is 0 since the car is not speeding up, not slowing down. Now this fourth graph, this one here, is just the combination of all these graphs. So from this point to this point, you see that's uniform acceleration. From this point to this point, constant velocity. That means acceleration will be 0. So let me just put the signs. From this point, let me call this A, B, C, and then D. So along AB, acceleration is positive, right, since it's speeding up. Along BC, acceleration is 0. And then along CD, acceleration is negative since the car is coming to rest and then slowing down. So if you know this, then finally, before we solve a question, now the next thing you need to know is the distance covered in this journey is the area. So consider this first part, the area under this slope, right, will give us the distance covered in the journey, right? So that would be the area. So we can just solve. Let me draw a line from this point. So you see that this is a triangle. So the area of this triangle would give us the distance covered in this journey. In the second part, the distance covered will also be the area under this graph. The distance covered there will also be the area under this graph. And for this third part, the distance covered will be the area under this graph. So remember that the slope gives us the acceleration, while the area under the slope in a velocity time graph gives us the total distance covered during the journey.